right, everyone, come on, let's get this over with, okay? The first real no-show Friday, huh? Should we have a quiz?
Yeah.
Don't tell anyone, we'll just pretend.
Did I get anyone with that last time? No, bad joke, huh? Yeah, I didn't know. Anyway, all right, so I do have your homeworks right here, and I don't have the average, by the way. Your averages are dropping a bit. You're getting a little lazy. One last homework, so don't get lazy. Remember, it does count as a test. So I don't quite know how much you got, but as I told you, it dropped a little bit. So I know we're almost near the end. Just don't get lazy, all right? You just have to do just a little bit more, all right? And today I'll go over what we did before, some new material, and then we're going to switch radically on Monday. And then as for what we do the week after that, I'm not sure yet, because this class, you folks were such good students that this class went faster than normal. So I'm a little bit stuck on what we're going to do on the last week, but I'll figure that out today. And I'm not going to cancel class. I mean, there's no way in hell I'm going to do that. Because I actually calculated, if I cancel class, say that last Monday, Wednesday, before the review on Friday, which is a hell of a thing, I will review this entire class on that Friday. Oh, that's a lot of fun. If I was to cancel that Tuesday and, that Monday and that Wednesday, that would be $40 out of your pocket. You all paid me $1,000 to take this class, and if I go cancel class, that's $20 out of each one of your pockets per day. For all of you, that's $4,000. So I would rip off the school $4,000 if I said cancel class. Yeah, I think I'm going to get in trouble if I do that, all right? So for my own neck, I'm not going to do it. So we'll figure out what we should cover on those last 2 days in case you checked out the calendars. I have some empty days there. I do have your homeworks again. I'll return those in between the 2 hours. And in the second hour, I do have a full lecture prepared. I just prepared it an hour ago. It's about distributions and calculating averages the correct way. I already warned you that you can't take 10 numbers and add them up and divide by 10. That is something we teach you in grade school, but it's not real. I'm going to show you the real way to do it. And also some other general calculus things you're going to run into in 346. So you're all going to take 346, except her, but anyway, you get the point. So yeah, I don't have anything else to talk about right now. Does anybody any questions? We're all okay. I know this material is terribly simple, and it's going to even get more simple. I'm glad that the hard part is done. It's just sometimes, I need to let your chin rest, okay? So, no questions? We're set? We're set? Looks like we're set. Okay. All right, now let me remind you that we're going, well, what we talked about last time was degrees of freedom when you have reactions going on in that special metal box. And what we found, the point of that was to understand why you have to subtract off degrees of freedom being the number of intensive variables, but that doesn't really work because, again, if I have a 50-50 ethanol water solution, I've decided one, but then I don't get to decide the other. It's already been set. That made sense, but then we had that chemical potential thing. Why do chemical potentials have to be subtracted off? The answer was that you might actually control chemical potential, whether you know it or not. And that was especially when you form a gas. In all those examples where a gas was formed, I showed you that if you put it in a small box versus a big box, that is a level of control. You're controlling the chemical potentials. And by control, I mean you're setting them. You could put it in a small box, you could put it in a big box. And depending on what you chose to do, you change the result. That's a degree of freedom. And we found that if you have extra phases, again, with a gas phase, in all the examples I gave, that was an enhanced degree of freedom, so it kind of made sense. So I have a couple of questions on your homework, and I forgot to do this last night. I meant to do this last night. I'll do it as soon as I get back after 4 o'clock. I have several more examples of reactions, really complicated reactions, and I showed you how to calculate the degrees of freedom. Basically C, right? The number of components from the number of constituents, and degrees of freedom, and then you can answer your homework, and I'll have one question on the test. So that's all fine and good. I don't really care too much about that stuff, but it's there. It might be on the GRE or something. But what we got into last time was talking about, again, equal chemical potentials. And here, let me, don't even draw this. Don't waste your time. Just about, as I introduced, we're about to figure out how to start with say a triple point, like on your homework. I'll give you a triple point, and then you can give me these points on a line. You can map out the whole thing if you feel like. But of course, I've asked, I said, okay, here's a triple point. Tell me where something boils, and that means like, look there. What is that point? Tell me where something melts, and then that's that point. Now again, I could have done that 100 times, giving you 100 points. You can build this whole face diagram. I didn't do that for obvious reasons, but anyway, you get the point. So what we're building towards is making this map. And again, I know I talked about gases in a box, but let's forget the box. Most things don't occur in a box. We work in a world of constant temperature and pressure, which means that dG is the most relevant, and I'm just doing this from memory. Minus SDT plus VDP. Oh, that's right. So that makes G a function of temperature and pressure. And then all we have to do is divide by number of moles. And then I have the change in chemical potential. Again, it's that easy. Again, that table in the back of the book, having everything per mole makes those formation delta G's automatically formation chemical potentials. It's just like magic. Divide by 1, and magically I've got chemical potentials. All right, now let me remind you that the change in chemical potential, and I want to know the change in chemical potential because I want to know why the solid turns to a liquid, or the solid turns to a gas, or the liquid turns to a gas. And that was, again, I didn't do this as a function of temperature. And again, you just have to map this one-to-one from what I'm doing right now. P constant T. Okay, and what we went over last time was that I want to look at each one of these individual pieces. And I said the change in U, the change in temperature, the constant pressure. I'm not going to repeat this, but it ends up being the change in entropy divided by the change in moles, which was just the molar entropy. Sorry, minus, right? There's a minus sign right there. Right? Don't forget that comes from the Johnson transforms, right? So, and then I brought up the reason that, if I have 4 cats in 2 rooms, if I lose a room, I've lost 2 cats. And that's because I have 4 cats in 2 rooms, which is 2 cats, right? It's the same thing. So that makes sense. And I'm not going to go over that again. It's kind of obvious. Now, what we did with that, okay, now this, folks, this is a really hard diagram to draw. I'm going to be really careful because I know to be careful. So, just go kind of slowly with this, all right? I don't know what to tell you here. Let me do chemical potential as a function of temperature. Now, this is what I drew last time, but I'm going to add the second part to it. So I'm going to be very careful how I draw this. So mimic me as best as you can, or just wait till I draw it and you see like, oh, that's what he was doing. I like it. Okay, so again, if I draw the solid, I'm going to have a negative slope, which is actually the answer for one of your questions on the homework. And it's not going to be a hard slope, that's a hard slope, that's a weak slope, it's going to be a weak slope, because solids don't have a lot of entropy. Liquids have a lot more, and gases have a hell of a lot. So those always slope down, and it's good homework. Anyway, number 1. And, I just blew it into line now. Okay, so let me do a solid. Again with a very weak negative slope. And again, I told you last time that at low temperatures, I always have solids. I mean, there's no tricks, all right? You know that. And so I know that the chemical potential of the liquid is higher. Of course it's higher, because at low temperatures, I have a solid, not a liquid. Now, I know that the liquid starts higher, but slopes harder. And so therefore, it's going to come down at some point. Again, I have to be very, very careful how I draw this. Okay, so there we go. And again, this is the fusion temperature, that's where the solid turns to a liquid, right here, at whatever pressure this is at. Now, let's do the pressure bit. Okay, so that means that, again, this is from the side, the change in chemical potential with pressure at constant temperature is going to be the volume per mole, or VM. Okay, now, again, this is the hard part. Let's say that this is at low pressure. This line. Again, I measured the chemical potential of God knows what. Let's make it most things, like ethanol, my favorite liquid. And no matter what, it slows down. And if I increase pressure, because I need to create a pressure versus temperature map, then I'm doing the solid liquid line right here. I need to change pressure and then look at where the crossing point occurs and map that change in pressure to a change in temperature, and then I'm building this line. All right, so that's the point. Okay, now most solids are smaller than most liquids. So if I melt ethanol, I have a big block of something I want to lick, and then it turns into a small thing that I drink. All right, so that means that the change in chemical potential, for one, if I increase pressure, chemical potential will go down, right? Don't you know me at this point? No, chemical potential goes up. But if the volume is small, I'm not going to get a big change. But then if something expands a lot, then the change gets bigger. All right, so in other words, let me increase pressure and do this. So that's not a really big change. Let me increase pressure a little bit more. And again, I don't have really that big a change. And then when I look at how this line changes, because it's a liquid and because it's bigger, like almost everything except water, then the spacing between these lines are much bigger than these lines because these are solids and this is a liquid. And the liquids have bigger volumes per mole, so the spacing is bigger. So let me draw that like that. And again. Okay, now what I'm seeing here, let me draw my P versus T diagram, is, now forget what I drew up over there before, because, I mean, you're going to get it in a second. Okay, here's the critical region, gas, liquid, and solid. Now what I'm seeing here is that the solid will melt at higher temperatures if I increase the pressure. Higher pressure, higher temperature equals positive slope. That's this, right? I know I usually draw it this way. I'm going to explain that in a second. But for most things, it's like this. Because most things will melt at higher temperatures if I increase the pressure. Right? You know, if I climb up Mount Fuji or whatever the hell it is, and again, this is almost everything except water. Water is very unusual. The density of ice is actually less than that of the liquid. That's very unusual, right? Normally the density of a solid is much higher than that of the liquid, but ice is opposite. And that's actually why I was watching that video a while way too much. If the density of ice was greater than that of the liquid, like most things, then what would have happened was all the ice that floats in the water, of course, would have gone to the bottom, would have stayed there, and eventually it would have climbed up till all our oceans freeze and we're all dead. Let's hear it for global warming. I'm so glad we killed ourselves. Anyway, so, all right, now let me do the opposite. Now let me do water. Right? And water, you know, water is unusual. It's only one chemical, but it's pretty important. Okay, so again, this is a hard thing to draw, so bear with me. So you see why most things slope to the left. Let me draw chemical potential. Sorry. Sorry, another aspect. Chemical potential versus temperature. And, okay, so now, again, water's solid ice is more sensitive in terms of chemical potential to pressure than the liquid because it's just simply bigger. And you can kind of think of that like Le Chevalier's principle. If I'm pushing on it, it pushes back harder because it's bigger, right? And that kind of makes sense. Okay, so that means that these spacings at low pressure are going to be pretty wide. And I'm drawing that horribly, I know. Whereas did I screw this up? This is really a pain in the ass, by the way. Now, that's for the low pressure, and that's a solid. Okay, now let me do the liquid. Okay, now the liquid spacing is much tighter. I'll date myself in the corner, I always do. And if you look, these fusion temperatures, if I increase pressure before, the temperature clearly rose. But here, if I increase pressure, the temperature is going down. And that means that my P versus P diagram, and again, remember this is liquid water, just write that down. That actually slopes negative. There's a critical region, gas, liquid, solid. Yeah, let's look at this. So, again, when I increase pressure, then the liquid solid line occurs at lower temperature. So I increase pressure, and sure enough, temperature is going that way. And again, that's important. It only occurs basically for water, but water is pretty damn important. So there you go. That's why I drew this the way I did, in case you were wondering whether I sloped left or right, and depending on whether I was talking about water or not. And again, water is pretty important. So, anyway, that's kind of neat. It also is relevant to your homework question. And now what I want to do is kind of, if I had this on a test, it'll be on test 3. It won't be on the final because, I mean, this is kind of instructive, but it's kind of hard to draw at the same time. So let's kind of just maybe think about this for test 3, but don't think about it for the final. What I want to do now, as I promised you, is let's actually develop the equations to draw these lines out. And this is very like exponential like, and this is very linear. Again, there are reasons I draw this the way I do, not just because I have the actual data, which I never show because I don't have a PowerPoint. Let me start on the new board. So again, the point of this is to actually write out the equations, which is also part of your last homework. I'm definitely not going to do well, depending on what I go over on the last few lectures, I haven't figured that out yet. I may have a problem set 11, but it won't be due. I'm not going to make it due because I just can't break that much at once. And so anyway, so this last bit is on your last homework. And again, remember that these lines are drawn at equilibrium, and I told you last time about how you can be out of equilibrium, that's cheating. So we're going to be at equilibrium, and if we're at equilibrium, remember our phase designations, and the phase alpha is equal to the phase beta. Okay, so remember that we use Greek letters for phase, who cares, doesn't matter. And again, I'm going to be a constant temperature pressure world, because I draw this as pressure versus temperature. Again, I'm going to be using delta G formalism, which is fine. I mean, I can pick any formalism I want. I might as well pick one that's pretty freaking relevant, right? So that means that entropy dt. Now, temperature is temperature. I don't think temperature depends on the phase, but the entropy sure as hell does. And I need to do this per mole because I'm really talking about chemical potential. It's not that big a deal. Once again, I can just get the entropy per mole and it's automatically the entropy per mole, the number I'm looking for here. And then the same thing, again, the volume per mole is going to depend on the phase. It's like how ice is bigger than the liquid water, and dP. And then I'm going to do the same for the beta phase. Beta dP. And remember that these changes in temperature and pressure are going to be the same because I'm on on the line. So we're talking about the same changes per phase. So just weird to disconnect them. Okay, so now what I'm going to do is I'm going to take alpha, and I'm going to subtract the beta. And now I have one thing in common, which is the pressure. And then let's see, I'm going to take alpha minus, all right, if I bring alpha over here, then that becomes positive, and I'll just let the beta become negative, as it always was, and I have a change in temperature. And now what I've got is dP. Oh, in case you can't see this, I'm afraid some of you can't see this. dT dP. No, what am I doing? dP. There we go, dP dt is equal to, and I'm not going to, oh hell, I'll just write it out. I'm feeling generous today. Alpha minus beta over B per mole alpha minus B per mole beta delta S per mole. Handwriting, that's a good thing. Delta B per mole. So there you go. All right, so now here's the thing. I've got the change in pressure versus temperature, which is the slope. Now, the name of the game is to, of course, as we know, that this is no different than A over B, and so I can bring A over B is equal to C is equal to A times B times C. So I can say the change in pressure is this times the change in temperature. Partials have to be integrated, which is going to be a big part of the next hour. Partials have to be integrated, but the damnedest thing is that integrals generate, okay, here's the integral plus a constant, right? Because the constant disappears in a derivative. And I always think of integrals as opposite derivatives. This is why, when I do the derivations, which I should do if I'm not too loud now, that's why I have to give you a starting point. When I integrate this sucker to get P versus T, I bring dt over here and integrating both sides, I'm going to have a constant, and that constant's going to have to be a point on this line. And that's why I have to feed you that. Now, of course, I said to you last time if you go to grad school, I tell you how to solve this without any constant points, but that's for grad students, so let's not worry about that. Okay, now I have a problem in that the change in S is always a pain in the rear. Yeah, I can look it up on the table, but I can also do something else. I've already committed myself to living in a constant P and T world. And so, and I know that entropy is heat. So at constant P, heat is what? Enthalpy, that's right, enthalpy, delta H. So, let me remind you, okay, because I like to go way back. ES. So I see that enthalpy is a function of S. And I always remember enthalpy is the one that's all positive, EDP. And constant P, you've already invoked that, that's gone. And therefore, the change in H over T is the change in S. And then I can integrate both sides. And I can do that because both are extensive. And therefore, delta H over T is delta S, which is what I'm seeing right there. And I divide by the number 1 mole, which doesn't do anything, right? Okay, so therefore, dP dt is delta H. Okay, so a little bit of IUPAC symbology here. I have the change in some kind of transition, okay. I'm not going to make a big deal of this. I don't care if you get it wrong on a test, but melting is fusion, boiling is vaporization, and sublimation is sublimation. There's no other word for that. Okay, so fusion, that's the vaporization, sublimation, that's easy, but fusion is melting, so that's the weird one. Okay, H per mole, which I get off the table in the back of the book, I divided by T. And then I got to use the same symbology for volume. Okay. And then again, I'm going to bring this sucker over here, integrate both sides, and then I've got an equation for the line, given that I have a starting point, because I have a slope. I've got the slope, but I need to know where to start. Again, that's why this is a little bit wonky. Okay, now I've got 3 lines of this. Look at that. I've got 3 lines. I got solid gas. Yes, I've lost weight. I've got liquid gas, and I've got solid liquid. So I've got 3 lines to describe. Now, 2 of them are going to be different than the other. I can see that I've got only 1 transition to liquid, but I've got 2 to gas. So 2 are going to be different than the 1. So let's do, what am I doing? Solid liquid first. And I don't think I can't remember for the life of me whether I did solid liquid with your homework. I don't think I did, but I can put it on the test, which case, by the way, these are giveaway. Almost everything we've done this last half is a giveaway. I'll write an equation. The only question I can ask you on it is like give you numbers and have you do calculator work, which is great because you're going to nail it, right? That's going to use a calculator, which is the case. You shouldn't be here. So let me break up our dP and dt. And I'm talking about fusion. And I'm talking about things melting over delta fusion. And these numbers I have to give you. I mean, you can't. Again, the point of physical chemistry is to figure out how to calculate these values. Just knowing what the molecule is, and that's why you go to grad school. Yeah, and then I'm going to bring you over to dt, which of course that's why I'm saving the t for last. I'm bringing it over there so that I see dt over t. Now we integrate, and remember that the units of the limits of an integral must have the units of the partial. I don't know, ask Isaac who discovered this stuff, right? And so we need P1 and P2. Now note here that P1 doesn't have to be 1 bar, and T1 and T2, T1 does not need to be 298.15. It's going to be, it's just sensible to use the triple point as that starting point. That's obvious for Brazilian reasons. And so what you get is P, sorry about this, sorry, let me do it this way. So therefore, P2 minus P1 is, oh yeah, there's nothing, change your x over x. All right, I got this crap, Fusion per mole over the same with volume, which is given to you. Then I've got natural log of T2, T1. And again, I don't need to start with SDT in this case. And also, let me point out to you that I warned you of this when we got to this material, is that when you're doing this stuff, stick to STP. Stick to SI units. You don't want to be plugging in kilopascals and liters. That may work, but it may not. I mean, you can't count on the PV equals nRT, that wonkiness, that P1, B1 equals P2, B2. You can't do that with this stuff. Stick with SI. I guarantee you, if you don't, and if you try to get funny with atmospheres and liters and all that jazz, you're going to get all of this wrong. So don't screw that up. Meters cubed, pascals, right? Joules, not kilojoules, joules. Now let me point out that how do I draw this? So I've got P2, I'm sorry, P2 is like Y, and T2 is like X. You don't even have to write this down, by the way. I just want to make a point. I want to make this look familiar. P2, P1, just write the same thing. Just brought up P1. That this looks like Y is mx plus b. Now that's because natural logs are actually kind of linear-ish, especially at low values. Natural log, when T2 is very close to T1, then the natural log might as well not even be there. They're actually very, very close together. So again, natural logs are very linear. So that's why I can say this is like Y equals mx plus b. And that's why on, and don't draw this again. Well, here, let me just toss this up. Hold up the board. Now, the point of this is, there's a reason that I've always drawn these as lines, like for most things, or for water, which I deleted. Again, these are very linear, and so that's why I drew them this way. And also, let's look at the slope. Now, fusion ages tend to be pretty big. It takes a lot of heat to melt something, especially a rock. Especially if you watch how it's made in the mornings, which I do. And now, changes in volume of melting tend to be kind of small. It's not like something expanded to a gas, that's big. But when something melts, its volume generally shrinks, unlike water, generally shrinks. And the change is negative, but it's kind of a small number. So I got up here, I've got a big number over a small number, which means that it slopes hard. So that's why I always went like boom. Or if it was water, water with this small negative delta V slopes that way and hard and like a line. So, okay, now what can I ask you want to test? I give you a triple point, I give you H's and V's, I give you T1, give you a T2, give me a P2, oh God, don't fall asleep. Anyway, so, giveaway questions, but that's how it works. Let me do vapor liquid and the vapor liquid and solid vapor sublimation. And I'll end, actually I'm going to end a little early today. I'm not going to go into the next subject today because it's too different. Next subject is, I believe they're multi-component phase diagrams, and God knows the engineers, and maybe you already have this, so if you don't want to show up, make it a no-show Monday. I get it, but I also might use language, chemistry language that you engineers don't use, so you might want to stick around for the video. I don't care. Okay, so let's do vapor liquid. Okay, and just so you know, I know it's boring as hell right now, because I'm actually bored even though I'm talking. I'm going to actually tell you about other types of phase transitions after this, so it's kind of a little bit interesting. Let me tell you about superconductors. So let's just work through this bullshit right now. And okay, so let's do this. Let's do DP, DT. Now we have to get the transitions right, and that's vaporization according to IU pack per mole. And I'm doing the symbology correct. Notice I didn't put a little circle there because I don't know that I'm not necessarily at SDP. That was not a stipulation in terms of this part of the class. And I've got the volume per mole. And here, here's the funny thing. Now this is going to be a lot different. This is still a big number. All right, when you phase transition something, it takes a lot of heat. You know it's all right, melting butter is not hard, but most things aren't made of butter. Most things are made of rock, right? So it takes a lot of energy. But when you are taking a rock and melting it, there's not a big volume, but when you take that liquid and make it a gas, this guy is overwhelmingly large. How large? It allows us to make, let me just point out this, that the M is a mole of a gas times the volume of a liquid per mole. Okay, so as I told you, one thing I don't quite like about this section of the class is all the approximations I make. I'm about to make one. Who would like to guess what it is? I'm going to turn this into that or that. That's right. Now let me just show you exactly how bad an approximation this is. Let's take H2O. Let's have 1 mole, which is 18 milliliters at about 0 degrees C. And even if it's cold, I can still make a vapor out of it because the vapor certainly has some chemical potential. It's certainly much higher than that the liquid, and that's why most of it stays a liquid. Wants to turn into solid. But regardless, as P equals nRT, it's 22.4 liters if it's a gas. And this is a liquid. Not that different from a solid. Okay, so let me take 22.4 liters minus 18 milliliters. And yes, I'm intentionally including the units to make you plug that into your calculator correctly, like you will on the final. Okay, so how much is the correct answer divided by an approximation? How different are they? They're not different at all. Again, plug it into your calculator if you don't believe me. You just get the units right. Screw up units, you're dead. So to approximate this as the volume of the gas is correct 2.1%, which is fine by my standards. So what I'm going to do is insert the volume of the gas here. So what I'm going to do is, I'm going to make that little swivel, and now, here, let me go, sorry I'm being a little wonky today. Sorry, what's wrong with me? The swivel is Z, and that's going to be RT. Right, and the moles are gone because this is per mole. Okay. So that then makes this sucker here. Again, I have to always provide you the enthalpy of vaporization times pressure over R over RT. I've got another T, so that's T squared. Okay, so then what I end up with, I'm not using the board at all today. Okay, so therefore, so I'm continuing from here. Change in P over P is, again, the vaporization, H per mole, R, T, T squared. And of course, I'm going to integrate that sucker. Like so. And now I just want to point out, let me do another aside. The change in X over X is the change. Normally I go over this, the mathematical proof of this, but I won't do it now because it's stupid, it's easy. Anyway, you've had this at some point. Got to use it a couple of times, so therefore I know that this is whatever my nose, change in ln t is equal to the change, same bullshit, write it again, do that if you don't want, t over t squared. Now remember that, again, one of the bigger lessons, especially when you're in 346, is that your limits have to have, that your limits have to have the same units as the partial. In this case, it has no units. It doesn't matter. It's still natural log. So I have natural log of P1. Again, that will be the triple point, natural log of P2. And this has units of T, so it'll be T1 and T2, where T1 is true because of T1, and T2, P2, blah, blah, blah. Anyway. Okay, so this ends up being, ln, so this would be lnP2 minus lnP1, and you're college graduates, you know that's lnP2 over P1. You're not college graduates, you're going to be college graduates if I do my job, and that's equal to minus vaporization H over R. Okay, so now I've got the integral of 1 over x, and I think the derivative of what is, I have the integral of 1 over x squared. The integral of the derivative of what is 1 over x squared. I'm thinking 1 over x, x to the minus 1. The derivative is minus x to the minus 2, so I need to add a minus sign. And I know that therefore I've got 1 over x from x2 minus x1, 1 over x2 minus 1 over x1, which is 1 over t2. 1 over T1. I can't get the calculus in my head, but it's really, we had it in high school. Okay, so what we can also then say, okay, so this is the answer. When it comes,
I
hear you very well, by the way. When it comes to answering questions I have on the test or the homework, which they're on the homework, you just plug in numbers. All right, again, this is a gift horse. But now, what I want to do is understand a bit about, sorry, delete this, why I draw things the way I draw them. So let's see the 3 again. Again, don't even write this. Right? I told you that why I slope, let's do water, why I slope hard, and to the left for water or to the right for everything else. But look at this. I don't know if you've noticed it, but I've been very careful to do this. The whole time, you've noticed that, Now you're seeing it more closely. Why was I always careful to make little curly cues? That's because I can say P2, which is just pressure on the left, by the way. P2 is P1, and this is basically a answer to one of your homeworks. So I'm going to raise everything to the E power, delta H. I'm going to put that, vaporization. Okay, so there's that. Now, negative exponentials do this, they go down. But T2, I like to start at the triple point and then I go up. Okay, that means that T2 will increase and so will P2. And if T2 increases, then 1 over a big number minus 1 over a small number is a negative number. So this is e to the minus a number, which is e to a positive number. And like e to a negative does this, e to a positive number does that. So that's why I draw these as growing exponentially. Sorry, like that. So one's like that, the other's like that, which is how I do it. And they will increase by delta H, which is actually why I've always tried to draw these as increasing harder with the vapor, because vaporization ages tend to be bigger. That's why this is like a slope. That's why I do these as harder rises than these. So, and whatever, look. Just fill in the numbers. Even if you don't give a rat's ass about any of this. Yeah, fill in the numbers. All right, so I got about 5 minutes left. Let's do something that other than watch ice cubes melt, because I've been boring beyond belief. God, I should have canceled class a month ago. Let me tell you about all kinds of other phase transitions that exist. I brought this up once, I don't know if you remember, but I talked once about phase transitions of soap on a surface. And I told you about how heat capacities go to infinity at a phase transition, and how we can actually measure the heat capacity of liquid at its surface. We actually do that, which is pretty incredible. And how soap undergoes phase transitions. There are all kinds of actually really cool types of phase transitions that are really fascinating. And go to grad school and study this stuff, or work at McDonald's. Hey, it's your choice. Anyway, so let's talk about magnetic phases. Magnets have phases, right? I mean, I know that there's solid water, liquid water, oh, come on, whatever. But magnets have phases too, and that's really kind of interesting. And especially if you have a magnetic field, which is always labeled as a B field, and it's pointed this way. Now, what I'm going to do is I'm going to take a lattice, three-dimensional lattice. Magnets are solids. I can hold one in my hand, but I'm just going to have to like slice it in two and show you what's kind of in the middle. I know that if, so this would be on a square lattice. I'm not sure what that corresponds to. This is technically phase up, and what it can do is go phase down, especially if I drive it with a magnetic field. Or maybe it does the opposite. I hate to admit I don't quite remember what it's going to do. Okay, so the thing is, though, that when it made this transition, at some point, it had to be in a different phase. It had to just be different. And these are different phases, and this is the phase transition. Now, what's important about that, I'm going to get in a second, so you're probably thinking, well, who cares? All right, okay, spin up or spin down, those are different phases. They are different phases. And trust me, it's shockingly important for a very good reason. But I'm getting there. Let me tell you something about that was learned when I was a postdoc at MIT. So this is a square lattice. There are copper ceramics do this. Copper is spin 1/2. That means it has a spare electron. Electrons are either up or down. It can get more complicated for other atoms, but for copper, spin up or spin down. So again, these are my copper lattices. When I was a postdoc, the guy I worked for now at Harvard, Dave Nocera, he had a student create a mineral that looked like this. It was a copper, and then back here was another copper. Oh, I guess I shouldn't call that. Now here's the thing, that this guy wants to be antiferromagnetic. In other words, if this is spin up, then this guy wants to be spin down. Right, that's antiferromagnetism. Antiferromagnetism. That's most things. Those are metals that are not magnetic. That's aluminum, right? Aluminum is not magnetic. Copper is not magnetic, right? This is copper. Someone tell me, what do I do here? You see, I got a problem. Spin up, great, not good. Spin down, fine, no. What do I do here? You see, there's no solution. There's no solution to this. It's called spin frustration. It's when you build a lattice where things want to be antiferromagnetic, but they can't be. Now, what was figured out right when I arrived at MIT, and again, this was 2 years ago. Sure. Well, that kind of hurt. But anyway, here's what they figured out. Here, let me draw bigger. And you don't have to be writing this stuff, by the way. I just want to make this stuff, I want to show you that this stuff actually can be pretty interesting. Let me draw it bigger. I kind of have to. What happens is that spin up or spin down, they tilt. They tilt towards each other. Now, you can do vector sums in their head. What's the total vector? 0. Right, because it can't become 0 this way. They tilt and become 0 this way. And that's the solution. And it turns out that the reason that they made this stuff is because it's a good model for superconductors. And superconductors, again, are like this. Let me draw this more accurately. So again, it's a copper. So this is called a Kagame lattice. Kagame like Japanese baskets, because they're used in 3 little forms. But anyway, your superconductor, your high temperature superconductors are copper on a square lattice. And it's kind of easy to do this. I'm just looking at each one. And notice that I don't have any frustration issues. I have no frustration issues. But here's what you do. You take your copper ceramic and you can literally blast it with ionizing radiation. And when you do that, you blow out an electron. Okay? So by the way, all superconductors or organic electronics, by the way, if I synthesize an organic electronic, I have to either ionize it or add like sodium ions. I have to do something to suck or add a charge. Let's do suck a charge away. That's easier to understand. Now notice what happens when doing this. All right, so I've made this material and I've wired it up. Now I need charge to move. And so the charge moves from here to here. I mean, literally, here's a negative electrode, here's a positive electrode, and I'm saying, hey, electrons go this way. But look at this SOB. If it moves here, hate, hate, hate. Lots of hating going on. They're haters, right? So that doesn't work. The electron can't do that. And it's not, by the way. But what can happen is this guy can do that, and then it's spin up. Like. But it has to do so from 2 sites away, not 1. Now, the way to do that is that these 2 guys pair up. These 2 guys pair up and they form a Bose-Einstein condensate, like I told you before. That's why you have to make this cold. These guys pair up, they form what's called a Cooper pair, and their total spin ends up being 0. And that means that this guy can flip with that guy, and then that guy goes there, all simultaneously. It's a very quantum mechanical thing. And that's how you get, I just told you exactly how superconductivity works. So, anyway, And this was a model for that, essentially, to try to build a simpler system to understand these processes. So my friend, a very good friend of mine, who synthesized this first guy who synthesized this stuff, they literally wanted to test its superconductivity properties by, again, ionizing the copper in the triangle lattice. We've already got square lattice, so they wanted to do it with the triangle lattice. So MIT has its own nuclear reactor, and to ionize things, you can just stick it up in a nuclear reactor. I swear to God, I'm not kidding. They got a stick. You know where this is going. They got a stick. They took the mineral that they synthesized and they stuck it at the end of the stick with some tape, and then they poked it into the nuclear reactor. I'm not freaking kidding. And then they pulled it out after a while, and some nuclear technicians did that, and then they put it in a box and gave it back to my friend. When he got it back, his nice little greenish mineral was like this black piece of char. And I was like, well, did that superconduct? I was like, man, what do you think? Did you think that superconduct? No, it didn't superconduct. So anyway, I am still obsessed with the idea of this guy with a little rock on a stick poking at a nuclear reactor. Like, come on, superconduct, you bastard. So anyway, okay, 10-minute break. I'm a little too long. 10-minute break. And if you don't feel like sticking around, that's fine. We're going to do 346 stuff. But